Um, so now I want to do the regular ray tracing, but for a slightly different situation. So in this situation, what we do is we look at a situation where D is now lesser than F1 plus F2. So F1 and F2 again are the focal lengths of the two lenses, but now D is smaller than the sum of the two focal lengths. So we now see that again, if we trace rays 2 and 3, you can see the dashed lines here would form an image P1 prime, but as we see, before it can form that image, the lens L2 is interposed before the rays 2 and 3 have a chance to meet. Such an object is of course a virtual object. So this object P1, this image P1 prime serves as a virtual object for the lens L2. So to find its ray tracing, we introduce a new ray, which is ray 4, okay? And I will talk about ray 1 later on. But ray 4 here is a ray that is obtained by taking the image point P1, or which is now a virtual object for the lens L2, and tracing it essentially backwards till it hits the point O2, okay? So that is one ray. So that is now redrawn over here on this figure. That's this ray over here, which goes all the way to O2. And since it must have originated from the same image object point, we can simply trace it all the way back to the object point. Okay. And so when it hits the lens L1, it has to bend enough to go back to the object point. So now we have one ray, which is the ray that went through the center of lens L2. We also have ray 3, which would have traveled parallel to the axis and hit the lens L2. So we see that ray 3 now, which I have now drawn in a solid line. And we know that this ray has to bend towards the focal point. And so we see that the focal point, the ray 3 will meet the focal point, and we now see that the image must be formed at the intersection of the rays 4 and 3. But you may ask, well, what about the rays 1 and 2? Can we use them to find the position of this image P1? And indeed we can, but the way to do it is to use the focal plane ray tracing that I introduced previously. So let me now, and this is not done in your book, but I wanted to show you that the focal plane ray tracing also works for this system. So let me now show you how that works. So we go back to the situation where, which I had drawn earlier. That is I've labeled all the rays as just as before on the previous drawing. That is on the top drawing of this slide. And we see the ray 2 would have met the lens L2 at a point which I'm calling B2. You'll see why I call it B2 in just a minute. Similarly, the ray that travels straight through the optical center of lens L1, which earlier would have met at the virtual image or the virtual object P1 prime, right? So if lens L2 were not present, then all these rays, ray 2, 3, 4, and 1 would all meet at the point P1 prime. And now I'm just taking the points B2 and B1, which is the points where these rays 1 and 2 intersect with the lens L2. Okay, knowing these 2 points B2 and B1, we can extend them backward till they hit the focal plane for lens L2. So this is the object focal plane. This green line here denotes the object focal plane for lens L2, right? And what I'm doing is extending the rays 2 and the ray 1 till it meets, of course, the ray 1 meets the object focal point right there. So let me just do it and you'll see what I mean. So I've extended the ray 2 and it meets at the point A2. And I also draw a line from A2 down to the center of lens L2, just as I did for the focal plane ray tracing in the earlier case when D was greater than F1 plus F2. Similarly, if I were to trace ray 1 back, it's going to intersect right here at the point A1. And I draw also a dashed line here, which is the line that goes from A1 to the center of the lens L2. So remember now, what we have to do is from B1, we have to draw a ray that is parallel to the ray from A1, the dashed line from A1 to O2. And I also have to draw a line from B2 that is parallel to the line from A2 to O2. So I've drawn those two lines. So the first is the line from B1, which is parallel to the line from A1 to O2. And the second is the line, this is parallel to the line from A2 to O2. That's this line from B2. And you can see all three of them meet at this point, which is indeed the image of the person at that point, and you can compare that to this earlier image over here, okay, as you can see. So indeed, as we see that, and as you can see, it's somewhere, not quite halfway between Fi1 and Fi2, and that's indeed also what you see from the focal plane ray tracing. And so both methods give you essentially the same answer, but I find the focal plane ray tracing is useful whenever we think about all these other rays that don't seem to be helping. So even without introducing any extra rays, just with rays 1, 2, and 3 that we are very used to drawing all the time, just by using those three rays, A1, 2, and 3, we can indeed find the position of the final image. We don't have to introduce the extra ray 4 to find the position of this image. So I find that a little bit more satisfying. So in this slide, I just want to point out that when D is lesser than F1 plus F2, you can quite easily sort of understand what is happening when you introduce another convex lens or another concave lens. As you can see from the way in which the rays are focusing, when you have one convex lens, the rays focus at the focal plane F1. When I introduce an extra convex lens, because the rays are still focusing, you can see that the action of the extra convex lens is to bend the rays further in towards the axis, because the convex lens introduces more convergence of the rays. And so the effective focal point will be closer to the lens. So when you have these parallel rays, it makes it quite easy to see exactly what is going on. So here the object you can think of as being at infinity, and that helps to see more clearly what must be happening. The total focal length of the system is now closer in. Similarly, if I add a diverging lens, the rays that were previously wanting to converge will now have a divergence introduced, and so their focal distance will be further out. And so we see that adding a negative lens decreases the convergence and increases the focal length of the total system. And you may be wondering, well, what about the situation when D is equal to F1 plus F2? Well, those are called afocal systems or telescope systems, and we'll come back to them when we discuss telescopes. I also want to introduce two other parameters, which are called the front and back focal length. It's quite easy to understand. The distance from the last vertex of a lens system, this is a compound lens of two lenses, but it could be generalized to more than two. The distance from the last vertex of the lens to the image point when the object is at infinity. So again, as you see, we have these rays coming in from infinity. This distance is called the back focal length. Similarly, the distance from the first vertex to the object when the image is at infinity is called the front focal length, and that is the FFL. And 1 over F is called the power of any lens, and when two lenses are in contact, the powers of different lenses add as shown. So indeed, when as D goes to 0, the front focal length and the back focal length become equal, and you can then simply just add the two focal lengths in this reciprocal fashion, or adding up the powers as they are called. The powers are just 1 over the focal length. 1 over F1 plus 1 over F2 gives you 1 over F when I make this distance go to 0. So that brings me to our first optical system, which is the eye. So first, let me introduce a compound eye. A compound eye is just a system where you have a single lens, which then focuses, which is called the corneal lens of these ommatidium, as they are called. The ommatidium is a single sort of ribbon that runs down the length of the compound eye, and each of these corneal lenses focuses the light down onto one little pixel, if you like, of what are called retinal cells, retinular cells. And these retinular cells and pigments allow for one pixel of the image to be resolved. So basically, a compound eye you can think of as having many different small pixels, each of them resolving one portion of an image and conveying that information down into these nerve cells, which are then wired into the nervous system of the insect. So that's what a compound eye is made of. And you can see that, for example, this is a rendering of what a flower would look like when seen through a compound eye and when seen through a human eye. And in fact, there are many insects in which there are lots and lots of compound eyes, or lots and lots of these ommatidia, and that can make this picture more and more well resolved. So having covered the compound eye, let me move on to the human eye. Here's a cross section of the human eye. Okay, so we'll start with the outermost layer of the eye. The eye is like a spherical, almost nearly spherical structure, and the outermost shell of the structure is called a sclera, which is an opaque and flexible and tough shell that surrounds the eye. The front portion of this eyeball is the cornea. Okay, and the cornea has a refractive index 1.376, and because it's the first interface between air, the air is outside the eyeball. It's the first interface between air and the rest of the eye. So a lot of the bending, because the refractive index difference is greatest at this point, that that causes most of the focusing to take place, or most of the bending of the light to take place. And it has as you can see, a sort of plano-convex appearance. This is actually good for spherical aberrations. That's something that we'll talk about when we do discuss aberrations. Around after that region of the cornea is the aqueous humor, which nourishes the inner eye, supports the iris, and the iris is this movable diaphragm in the eye, and the center region, which is a hole in the iris. This iris you can think of as like an aperture that you can close down, just like in a camera, and this hole in the center is called the pupil. Okay, and that also is responsible for the color of eyes, the pupil. After this region, we come to the crystalline lens. The crystalline lens is a little bit of a misnomer. It's really more like an onion with layers and layers, each of a slightly different refractive index. In fact, the refractive index ranges from about 1.406 at the center, which is very dense, to the less dense region, 1.386 in the outer cortex. So this should remind you of a Grin lens, the gradient index lens that we've already discussed. It has a smoothly varying refractive index from the outermost region to the inner region. So the fine focusing is then carried out actually not by changing the focal, not by moving this lens, but by changing its shape and altering its curvature. We'll talk about this a little later. Finally, we reach the vitreous humor. It's just a thick gel that gives support to the entire eyeball. And that ends up with all the light, as you can see in this picture, getting focused on this final layer, which is the retina. Okay, the retina is the detector on which all the light is falling and is getting converted to by photochemical reactions, and then being sent to the optical nerve. So here's a cross section of the retina. Sorry, that shouldn't be human eye, but the retina. This is a picture of the retina. This is an electron micrograph of the retina. And the retina is about 0.1 millimeter thick layer on the choroid. Okay, and it's supplied with nerves and blood vessels, as we just saw. It's composed primarily of two types of cells. One is rods and the other are cones. And the rods are much greater in number usually in the retina. They act like a sort of black and white film. The cones in the retina detect the color. And at the center of the retina, if you see here, in the very center of the retina, is a little region about 3 millimeters in in size, which contains about 2 times as many cones than rods. And even within that macula, the center of the retina is called the macula, there is a even further central region which is completely free of rods and contains mainly cones, and that is called the fovea centralis. So it gets you full color vision right in that region. And so as you can imagine, since the actual region where you get the perfect color vision, or as good a color vision as we can get, is the fovea, the eyeball is constantly moving to try and project light from the area that you're interested in onto the fovea. So this was actually a micrograph of the rods and cones in the salamander, and this is a actual micrograph of the human eye. You can see there are a lot more cells and so on, and you can actually see how dense this region is. Finally, the last topic that I want to talk about today is the accommodation of the human eye. So how is it that actually we see? How does vision work in a human eye? When an object is very far away, the ciliary muscle, which is ligaments that connect from behind the iris to the eye, they are attached to the lens of the lens that I just talked about. And what happens is when it's completely relaxed, when these muscles are completely relaxed, the lens is nearly flat. So the radius of curvature is large, and so it has longer focal length. And objects at infinity, and that focal length is essentially the distance between the lens and the retina. So we can see that an object at infinity essentially focuses down onto the retina. As the object moves closer, you must now change, since the image distance does not change, but the object distance is changing, we have to change the focal length of this lens. And that is done by these ciliary ligaments. As you can see them right here, they're contracting. And as they contract, the lens curvature decreases. And the focal length decreases, and that allows us to keep the image distance a constant. But as we keep decreasing this object distance, it turns out that we reach a point, if we get any closer than that point, that the lens cannot accommodate that object anymore and does not form a clear image on the retina. And so this closest distance of approach for an object beyond which it cannot be focused is called the near point. This is approximately about 7 centimeters when you're young, and keeps increasing like 40 centimeters in middle age and gets to about 60 centimeters by about 60 years of age. I should also mention that there are many other accommodation methods that are found in nature. So in some fish, the actual lens keeps moving in between the eye and in between the retina and the eyeball. And in other birds of prey, which need really good vision, they have much stronger changes in the curvature of the lens.